Okay, so this is the final part of your chapter 3, alright, man-made satellites. Okay, so here, I'm not going to spend too much time. I'm just going to go through some really important things. Alright, of course, first, here, the formula. Okay, now, linear speed. Okay, remember, this term is given when an object is in orbit, meaning it's orbiting another object. Alright, so when you move in the circular motion, the speed that you are using to move in a circular motion is what we call linear speed. Okay, so for linear speed, alright, only the radius is affecting the linear speed. Okay, basically the mass of the object will be the same, right? The only difference will be the distance. Okay, so it's either from here to here or maybe from here to here. So this one is R1 and this one is R2. Okay, but the mass of the satellite will not change, right? Therefore, the factor that affects linear speed, especially for a satellite, is only the radius. Okay, meaning the distance between the satellite and the Earth. Okay, and then since this is moving in a linear speed, okay, we can also conclude that the centripetal acceleration will be equal to your gravitational acceleration. Okay, so this one will depend. If here you calculate your G at this point, is let's say what they call 8.82 meter per second squared, let's say for example, meaning that your centripetal acceleration is also the same since you are moving at linear speed. Okay, so you need to remember the relationship. All right, okay, so the formula for linear speed, okay, again I'm just going to show you how we derive this. All right, and then again we have your centripetal force. Okay, equating both equations. Alright, cancel off common factor. Okay, and then the r you bring to the other side. Cancel off. So you are going to left with v squared equals to gm over r. And my linear speed will be this one. R. Okay, so this is the formula for your linear speed. Okay, and the only factor that affects is the radius, the distance. Okay, so that is it. Alright, so okay, what happens when the object, or what they call, if you remember when we learned about the what they call centripetal or linear speed of a satellite. Okay, how does a satellite orbit Earth, right? We say that they must achieve what they call a required velocity, okay, in order for them to orbit. And then I did mention, if your speed is not high enough, you are going to fall back to Earth. If it's too high, it's going to fly away. Alright, so in this case, when your linear speed is less than the required speed, what happens is that slowly the satellite will start to fall down basically. It will spiral down towards Earth. Okay, slowly they will fall down, and then once they reach here, boom, explode. Okay, like that. Alright, so that is what happens when the linear speed is less than the required speed or the optimum speed. Okay, the satellite will slowly fall and then enter atmosphere, and then because when you have friction between the satellite and the air molecules, you're going to produce heat, and then finally it will explode or burn up. Okay, so this is what happens when the linear speed is less than the optimum speed, okay, or the optimum velocity. Alright, alright. Okay, types of satellites. Okay, this one I took from the textbook. Okay, because I think it's quite good enough. Alright, so there are two types of satellites that is normally orbiting your Earth. Okay, one is what we call a geostationary satellite. Okay, okay, this one. Okay, geostationary satellite. Okay, and then the other one is what we call non-geostationary satellite. Okay, so each of these satellites, they have their own orbital pathway. Okay, so basically geostationary satellite, they are orbiting in what we call the geostationary Earth orbit. okay, or GEO, alright, or sometimes they put it like this, geostationary Earth orbit, okay, GEO, okay, meaning this is their orbital path. Whereas for non-geostationary, they have their own route, okay, their own path, their own orbit, alright, which is called an LEO. Alright, this one is depending on where is the satellite. Okay, non-geostationary, it can either be what we call lower than the GEO, or it can be higher than the GEO. Okay, not necessarily lower one. Okay, it depends. Alright. So the difference between the two satellites is like this. This satellite will orbit at the same time of your Earth's rotation. So in other words, you imagine that here I have a line attaching the satellite and the Earth. So when the Earth orbits, the satellite will also follow. Okay, that is why the satellite will be at this position. Meaning if the geostationary is above Malaysia, meaning that it will always and forever will be above Malaysia. Alright, since it will orbit together with the Earth. Whereas for non-geostationary, okay, you imagine they don't have any lines attaching them to Earth, so they are basically orbiting in their own way. Shock sendiri lah, basically. Shock sendiri. Suka-suka saja pusing. They don't bother about the Earth's rotation. Okay, so that is the main difference between the two satellites. Alright. Okay, of course you need to know a few examples. Okay, this one important. You must know examples of non-geo and also geo. Okay, and then what is it used for? This one is important. Okay, alright. So look at the summary here. Okay, geostationary, their orbit is GEO. Alright, same direction as Earth's rotation. That is why their orbital period is 24 hours, because they are basically following the Earth. Okay, and then always above same geographical location. Alright, whereas for non-geo, okay, it will either be lower Earth or higher Earth depending on where is it. Alright, so if it's lower Earth, meaning the orbital period will be less than 24 hours. If it's more than GEO or higher Earth, meaning it's going to be more than 24 hours since you are further away. Alright, so that is the difference okay, and different geographical location because they don't follow Earth's rotation. Shock sendiri. Alright, so that's it. Okay, the two differences between geo and non-geo satellites. Alright, next is escape velocity. Okay, so simply said, escape velocity is basically the speed that you need to escape from Earth, let's say for example. Alright, so different planets will have different escape velocity. Okay, Earth's what they call escape velocity is around 11,000. How much is this? Oh, okay, 11,200 meter per second. This is Earth. Okay, Earth's escape velocity. Meaning if I want to escape from Earth, if I want to go outside of Earth, I need to at least achieve this speed only I can run out. Okay, if not, you are going to stay on the surface of the Earth. That's it. So, very simple concept. If your velocity is less than the escape velocity, you are going to stay on Earth. If your escape velocity is more than the Earth, you are going to run away from Earth. Alright, so imagine if I can run at this particular speed, meaning if I start here, run halfway, suddenly I'm here already outside. You flying. Okay, so that's the meaning escape velocity. Alright, the speed needed to escape from the Earth, or what they call to overcome the gravitational force and go to outer space. Alright, so for any spaceship, satellite, alright, if I need to go to outer space, I need to make sure that my speed is higher than this. That is why they are using rocket and then the fuel. Okay, rocket, and then you can see a lot of fire coming out, right? The reason being is because they need to achieve a velocity higher than this, then only they can go to outer space. Okay, so how can we achieve escape velocity? Alright, meaning that your kinetic energy must be more than your gravitational potential energy. Okay, so it's basically telling you that you need a higher speed, then only you can escape. if your speed is not enough, you cannot escape. All right. So the formula for escape velocity. All right. So kinetic energy is this, half mv squared. All right. Then plus your gravitational potential energy. This is the formula. Okay. Now some will start to question why there's a negative sign here. All right. But I'm not going to dwell too much into as to why I have a negative sign here. Okay. To my students who will be joining my online class, of course, I will explain to you why. All right. So if I rearrange this formula here over r, right? Okay. Again, we are going to cancel off the common factor here. All right. So we are left with half v squared, right? Bring the half over the other side. What you're going to get is 2gn over r, and then square root. Okay, so this is your escape velocity. Alright, it's very similar to your linear speed. The only difference is that one you have 2, one don't have 2. Okay, so if they ask you to calculate the escape velocity, make sure you use the correct formula. This is the formula for escape velocity. Alright, linear speed is the one without 2. Okay, so don't get confused between the two formulas here. Alright, so factors. Okay, they'll always ask you this one. Which one will affect your escape velocity? Okay, let's say, alright, come on, let's be a circle. Okay, so let's say this is Mars. Alright, and I am here. I always like to be there. Okay, so if I want to escape from Mars, two things I must consider. One is the mass of the planet itself. Second, of course, is the distance. Where am I from the planet? Alright, so given the conclusion here, okay, the larger the mass, the higher the escape velocity. Alright, meaning if the mass of the planet is very large, okay, your escape velocity will be very high, meaning you need more velocity than only you can escape. Okay, if you are further from the planet, then of course it's easier for you to escape, right? Because your what they call attractive force is weaker, your gravitational pull is weaker, so easier for you to run away. So in other words, if I'm here, okay, and compare when I'm at here, alright, so here, okay, and here, so I'm nearer to the planet, so the gravitational force is stronger, it will pull you, right? So if I want to escape, I need more energy, more speed. Okay, that's why I need to increase my speed, then only I can escape. Whereas if I'm further away, since I'm further away, right, easier for me to escape. So I don't need to use that much of energy to escape. Therefore, the escape velocity will be lower. Okay, now when larger the mass, okay, remember, the bigger you are, the stronger the gravitational force. Alright, so if you have a very big planet, okay, the gravitational force will be stronger. So if the gravitational force will be stronger, right, your escape velocity will be higher. Okay, means that it will be more difficult to escape. Alright, so if I give you an analogy, if let's say this is Earth, our escape velocity is this one, right? Oh, sorry. Okay, this one is bigger, right? It's gonna be more than this one. Okay, so meaning it's going to be even more difficult to escape. I need even more kinetic energy to escape. Okay, so basically that is the two factors here. Alright, so if you notice, I only say mass of the planet. Means mass of the object is not really relevant. It doesn't matter how big you are or how heavy you are. Alright, if I want to escape from the planet, two factors. One is the distance from the planet and the mass of the planet itself. the mass of the object will not affect your escape velocity. Okay, that is why I highlighted here. Right, mass of object will not affect escape velocity because doesn't matter how big you are. All right, the main factor here is Earth or the planet. If I want to escape from the planet, of course I need to consider their size. Okay, how strong they are. If they are strong, harder for me to escape. If they are weak, easier for me to escape. Basically, that is the meaning here lah. All right, the what they call escape velocity. Okay, so why do we need to study escape velocity? Okay, basically this one is when you go into outer space. All right. For example, if you want to land in a planet, you need to know if you want to land or come out from a planet, you of course need to know the speed required for you to travel so that you can leave the planet. All right. If your traveling speed or your velocity is less than the escape velocity, then you'll forever be stuck inside the planet, cannot come out. All right. So let's look at a few examples here. Okay, Earth's atmosphere, meaning your gases. Why are they surrounding your Earth? Why the gas don't suddenly go into outer space? Okay, so the reason is because of your escape velocity. So let's look at the value here. I have certain values here. All right. So Earth's what do you call escape velocity is 11,000, right? Okay, you don't have to exactly follow my this one. You can fill in the what they call empty spaces on your own using your own style or whatever. Okay, just make sure you get the concept right. Okay, Earth's velocity is this one, whereas your what they call atmosphere or your gas particles. Okay, they are moving at a velocity of roughly 500 only. Okay, so your atmosphere velocity is less than your escape velocity, right? Okay, so means you cannot escape from Earth lah. Not enough speed, right? That's why your atmosphere will remain on the surface. Okay, so they are only going to what they call be on the surface on your Earth. They won't suddenly fly go into outer space. No. Okay, so that is the first reason. Alright, aeroplanes, why they cannot escape from Earth? Alright, basically the same explanation. Okay, but aeroplane, what is their speed? Okay, let me see here. Alright, aircraft, commercial aircraft. Alright, normal aeroplane. Okay, so normal aeroplanes can travel at around 250. Alright, even if jet, okay, they travel around 2,000 meters per second only. Okay, so no matter how, alright, your escape velocity here will still your velocity of your aeroplane here will always be lesser than your escape velocity. Okay, that's why your aeroplane, okay, cannot go what they call away from Earth. You will always be inside Earth, alright, on the surface of the Earth. You won't fly your aeroplane and suddenly you wake up, you will be in outer space. No such thing, right? Okay, the only way that you can go into outer space is if you use rocket. Okay, so how does this help? Alright, so basically if you see here, boom, okay, what they call a lot of fuel. Okay, if you have more fuel, you have higher thrust. Thrust, higher thrust. Oh, it's very better for you lah. Okay, meaning you have more power lah. Alright, so if you have this one, you are going to achieve a higher speed. Okay, so if I have higher thrust, meaning then I can achieve escape velocity. Therefore, the rocket can go into outer space. Alright, so that is what we need to study about escape velocity. Okay, that's it. Done. Okay, so calculations. Alright, so basically that is it for your chapter 3. Finally done. Okay, man-made satellite and Kepler's law. Alright, so I hope that throughout the chapter 3, I was able to help, even if not all, but maybe one or two of you. Okay, so the next part will be about heat. Alright, you're going to learn about heat, a lot of calculations there. Okay, so that is it for today. Alright, bye.